last time. So as what I described yesterday is the fact that if you rotate those things at exact counter rotation, that's the self-generation I described in all the mechanism. So what I will describe today is what happens when you do not rotate them at the same speed, and then there's a bunch of things that happen, and it's all in these 5 papers we've published on those things. The advantage here, I want to pay a short tribute to the people in Riga and Karlsruhe. First, because they did it, and I know bloody well what it means to do this. It's a very long effort, and then the other thing is contrary to these experiments, what you have here is 1 degree of freedom that you can tune concerning the flow geometry, and that is not so easy to do in other experiments. So the nice thing about those, for me, seeing these experiments in 2000 or hearing about it in Cargès from Agris, and Robert Stiglitz was there, meant that it was not totally foolish to try to go after the dynamo effect with a liquid metal, which is not a given. As I said, there's so many effects of turbulence that is not known that it could have very well not have worked. And the fact that it worked, and the fact that it was pretty close to the prediction, was something that was very interesting. On the other hand, the VKS stuff that I described yesterday showed the first interesting feature is what we got was not what we had predicted, which is always a nice way to get thinking about more interesting science. And the second thing is that we have one more control parameter. You can not only can you vary F1 equal F2, but you have F1 different F2. Now you can see these as being a blessing, because you can work now with 2 degrees of freedom, which is F and delta F, and there's some similarities that have been observed experimentally between rotating the 2 at different speeds, or rotating them at the same speed with the outer vessel rotating at the 3rd speed. Okay, there's some similarity means that in a water experiment, we built a water experiment where the other wall rotates, which is what you wanted, right? And in that case, you find that if you study the evolution of the torques for rotating at different speed or rotating at the same speed plus the outer vessel rotating, at least the torque have the same dependence on some sort of Rossby number. Of course, it doesn't mean that the flow is the same. It doesn't mean that the boundary conditions on all the layers have to be different, right? So there's some similarity between rotation and imbalance. So there's 2 ways you can think of it. One of them is adding rotation to the system. One of them is breaking a right-left symmetry. Okay, and of course once you can break a symmetry in the system, interesting behavior are supposed to happen, and indeed they do. Now, when you do that, before I describe anything related to the dynamo, one has to understand that when you break that left-right symmetry as well, you create a global bifurcation between 2 states. This is a very surprising feature, again, is that when you force this flow with the impellers rotating at different speeds, if you increase the difference in speed, for a while it would remain on a flow configuration that has that symmetry with the toroidal, the poloidal circulation like this, and the toroidal one which has opposite direction like that. But when you increase the dissymmetry too much, then what the flow does is it doesn't evolve continuously, it bifurcates, all right, to a sort of winner-takes-all type of configuration, where you have mainly one poloidal flow. Of course, there's a little one here, okay, and mainly one rotation. So think about F1 being kept constant and F2 decreasing. It will remain like this and to a certain point, and then the shear layer is going to move near the floor of this. Okay? It is not at all obvious that you have states like this in a flow at the Reynolds number 10 to the 6. All right?
Well, this isn't really a bifurcation, because this looks like how to say, continuous transition, simply a quantitative difference. What you showed here.
It's there.
It's okay.
It's there. It's there. That's exactly what's happening. If this is, don't worry. What those axes are just the dimensionless torque. Okay. And if you look, and they're associated to the flow as well. If you look at the imbalance, nearly finishing. Theta is F1 minus F2 divided by F1 plus F2. Okay? So if you change the imbalance here, you start from here, you perturb the solution. For a high enough value, you jump to that branch. Now that branch you can keep through all that regime and go back here. Okay? It is a global, it really is a global bifurcation.
What is delta K? What is represented here, delta K?
Delta K is just torque, dimensionless. It's the torque of motor 1 minus torque of motor 2. So when it is 0, they're driving the system symmetrically, and the torque that one of the motors has to apply is a very good mirror of the flow. If the flow changes, the torque changes by the factor of that. Okay? And this is very surprising. This is, by the way, this is a very interesting hydrodynamics problem on its own. Bifurcations, global bifurcations of system at a Reynolds number that high is not trivial. So that's what I showed you here is measurements that have been done in a very well controlled water experiment. Okay, first done by the group in Saclay, and then done by the group of Javier Borghete at University of Navarra, and this has confirmed the previous result. Borghete has built the most symmetric von Karman flow you can think of. Everything in his setting is within micron precision, because we thought at some point that those transitions might be induced by imperfections, asymmetries that are imposed by outside conditions. So his thing is, to micron precision, it is an exactly symmetric von Karman apparatus.
Is that a water experiment?
It's a water experiment, all right? And when he studied that, exactly the same global bifurcation was observed. So this global bifurcation is not due to the fact that we're inserting a little something here, or you know what I mean. It could be that, but it's not.
Could you check that by introducing an obstacle and see how much of a perturbation you would need?
It doesn't change. Mm-hmm. It doesn't change. We've changed that. But beside the perturbation, it's fairly easy to imagine mechanism by which, if there's any amount of, say, ellipticity in the vessel or stuff like that, you could introduce these kind of instabilities, right? But it wasn't the case. So now if you go to the sodium flow that has massive things installed, which is not perfect at all, which has all the problems of these flows, you see the difference here. It's a torque again, and you see the torque that is required to drive the flow near the slow disk, one cell, and near the other disk. And there's also that bifurcation from 2 cell to 1 cell. Now, it's not exactly the same hysteresis because you've messed things up. But for certain values of the imbalance parameter here, you bifurcate from a slowly evolving 2 cell to 1 cell flow. All right? So what I'm saying here is that it's nice to have an additional degree of freedom, but you have to keep in mind that that additional degree of freedom is also changing the flow. And it doesn't do it continuously, it does it with a rupture. There's two major types of flows involved in here. Okay? And it's for that's not explained at the moment. So here is a cartoon of what one sees in the experiment when you vary the frequency of one impeller and vary the frequency of the other impeller. So each of these points here is a measurement for set frequencies, and each of these symbols is, all right, what I've described before is no dynamo onset of a dynamo. All right, is these open symbols to blue symbol is the stationary dynamo I described before. Now what you can do is you can do several paths. You can start here at keep one disk constant and change its frequency, which is usually what one does experimentally. Okay, and when you do so, you cross different regimes. When you're close to exact counter rotation, you still have the dynamos. Okay, and the stationary one. Then you hit some point where this is the lower blue, the dynamo still exists but with a much lower amplitude. Now if you keep increasing the imbalance, we had dynamos that became time dependent. In the time dependent regimes, I'll show you, we've seen reversing dynamo, oscillatory dynamo, bursting dynamo, as main classes of objects. All right, this becomes a little clearer if I draw it as a function of the imbalance parameter here. Those are the stationary dynamos. You go away, you move to another kind of dynamo. You see the reversing one. Here you hit the boundary at which the flow bifurcates. Okay, so the flow bifurcates to something new. And you get another kind of dynamos that are, what do we have? Stationary and oscillations. And this is the kind, what I'm showing you here is for Agrisan. I've added that, this is the kind of crazy path you do experimentally. Decrease one thing, see what's going on, please increase the speed. No, come back, see whether you can track it. Decrease the speed. So these flying fly motion is what you do in the experiment, right? It's oscillating, all right, reduce again, see if it continues to oscillate. No, stop, we're losing it. So that's how you do it. So there's no way we can explore a parameter space like you would draw it nicely on the board, right? This is not filled with points. And each of these points here is the result of a path. I want to say this because immediately you're going to say, oh, wait a minute. In those instabilities, what you see is path dependent. All right? And in many cases, it is. So
But you want to explore the solutions that exist. Of course, some solutions, if you have multiples, are always accessible through a certain history. Well, and it's good if you have a record of this, but eventually you want to plot the bifurcation diagram, of course. Right. And that comes up, I hope.
Is there a possibility to set up a limit cycle to catch it and pin it down to one point?
Yes, there's some of this, yes. All right, so those are the dynamos. Now, if you do another experiment where you put more points, remember those are slow evolution. Each of these points is like half a day, okay? And of course I've been cheating because I've assumed that theta positive is the same thing as theta negative, right? So I only measured half of what I'm showing you. All right.
And that's okay, yeah?
I'm believing physics is all right.
I mean, you can check that in a few cases. Was okay, yeah?
Yes, it's okay. We haven't checked all of them,
No,
but
no.
it's reasonably okay.
Mm-hmm.
All right, otherwise I wouldn't do it. So you see at the fixed theta, you get some funny things. You go all the way up, you hit the stationary bifurcation, but sometimes you can go all the way up, and this is at a constant theta. What you do is increase, so it's one way we do it, I call Rm F1 plus F2 over 2. That's how much shear do I have as a measure. All right, you can increase it by much more, and you only heat the dynamo for high values. Let me show you what it looks like as a picture. So what I'm showing here is a recording of the magnetic field measured at that point, with red being the toroidal component, blue being the component along the axis. Okay? So we go like red is this one, blue is this one, and green is this one. Right? Green is it's at one point. Right? But believe me, when it oscillates someplace, it oscillates all over. It's not just one point that has an oscillatory behavior.
This would be a fantastic discovery, right?
But that doesn't happen up to what we know. So when you move A, B, C, D, E, F, blah, blah, you are increasing that parameter theta. Okay? So that's the dynamo I was describing yesterday, exact counter-rotation, toroidal, mainly toroidal flow with this n equals 0 dipole symmetry. You increase a little bit, you hit those irregular reversals, then you go to an oscillatory magnetic field, then you go to a stationary dynamo again, then you go to a bursting dynamo with burst of either side, then you go to buff, you wait for a while, and the dynamo is not doing anything, and suddenly it starts. So you believe that you just changed the temperature ever so slightly to go back to a threshold where...
Or the metro train passed by.
Yeah.
Or the metro train passed by.
Yeah, and you've bifurcated from one state to the other. And then at that same range of parameter, you have the Earth-like reversals, and then you have another bursting dynamo, and that's a stationary one with a high field. That's the stationary with a weak field. That's an oscillatory. And when you go to only one disk that rotates, okay, you've stopped one. So you're completely in that configuration. You again recover a stationary dynamo. I'll come back to it. So a small Riga is stationary field.
Small question.
Yeah.
In the plot G, there are these reversals what are more or less like. Is there a reason why they're not symmetric, or is it just because they on the upper side are much more?
Yes. No, there's no particular reason why they should or should not be symmetric. All right. If you would expect them to be symmetric, of course. Now, any imbalance in the thing, I mean, if you think about the Lorentz attractor, will kill you from being completely symmetric. And then the last experimental point is we've seen 1, 2, 3, 4. See what I mean? It's not like the thousand.
But panel B is symmetric, right?
Yeah, but panel B is closer to an oscillation than proper reversal. I'll come back to that again. Right? So, if you start from this, with these many different regimes, I cannot describe all of them in detail, and on top of that, we haven't understood all of them in detail. All right? So I'll describe a few that we've seen and a few features that may be helpful to understand that.
It's all measurements made with dynamo with ferromagnetic.
Yes.
plates.
Oh yes. Here is the ferro impellent. Right. All that I will describing here is made with that. Now, this is almost on a line with f1 plus f2 equal constant, all right? And you're almost, and you're increasing that parameter theta here. Now, before I go into a more detailed description, there's something we like particularly here is the fact that these happen in a small region of parameter space. You don't have to change the parameter space a lot to get various kind of dynamical behavior for a dynamo. And for at least for the physicist, I think it makes sense. If the planets and the stars have to have different behavior but still look the same from a distance, it means that the dynamics has to be reached. The internal dynamics, all right? And this is an indication, I'll come back to that in the description of how it behaves. It's the description, it's an indication that several modes are becoming unstable in a narrow region of parameter space. Okay? So there's a small range in Rm where you can excite several modes, and those several modes will interact. Rather than you have a bifurcation, then you have a secondary bifurcation to something more complicated, and then a third bifurcation, and that's only then which you hit chaos. All right? It's a simpler way to do this. Now, see from a different perspective with frequency of one, frequency of the other. You have a stationary with a high field, then you have pockets of oscillating dynamos that are separated by stationary behavior, and then you hit a region where there's very little action, and then you get hit again an oscillating dynamo, which reduces to a stationary dynamo when only one disk rotates, and I'll describe that. So here is the Earth-like reversal. The Earth-like reversal, they happen. That's the wrong. Yeah, they happen here. Okay. And what you see is so the joke is just copying the geomagnetic reversals to what is being observed. It's mainly a joke. But it shares some features. So the features it shares is that the magnetic field goes to zero during a reversal. The one that all the components of the field shrink and go to the other side. Now it's a work in progress to see if this is completely the case or if some energy has been transferred on to higher order modes. Quadrupole, octupoles, blah, blah. I mean, what happens? Then it has this very characteristic thing of when it changes polarity, it overshoots a little bit, it comes back to a stationary value, it reverses, overshoots a little bit, comes to another value, and then you have those other events that the geophysicists particularly like, which they call the excursions. That is, the magnetic field is decreasing, 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 and then when it is growing again with the same polarity. It doesn't reverse.
But then maybe here it is important to recall that it's measurement at one point, right?
It's a measurement at one point. I'll show you.
It helps to have this in mind.
Right, but it's in that particular case we did not have measurements at that time that were well resolved enough to know what the other higher order components do. So treat these as I'm plotting the dipole. Okay, so the dipole goes to zero and grows again, and these, from the several measurements we have, is exactly what's going on. Okay.
What is theta in this plot?
What is what?
Theta. Your theta parameter.
0.09. It's you're hitting the line where you change from here to here.
So it's the oscillatory regime number 1 near the diagonal.
It's yes. It's at the edge. It's at the edge of that.
Mm-hmm.
Okay. Alright, so if I play with it a second, this is the orientation of the magnetic fields measured at the point and as a result of correlation. It's just fun to watch. Now, one of the questions that one may want to ask just by looking at this is, what are the time scales? All right? Is the question, who did I ask that nasty question of how do you build the time scales for basic principles? So here is, the time is in seconds. All right? So between reversal, you say you have 100 seconds. All right? One of the questions is, how do you build 100 seconds from the measurements? So this is, say, for the reversal, this is rotating at 16 hertz. This is rotating at 22 hertz. Okay. The difference of none of these makes 100 seconds. The difference of this doesn't make 100 seconds. The diffusion time is a few seconds. Okay. The characteristic, I don't know, Haven wave speed, you name it. All right. Well, I haven't been able to build 100 seconds. Okay. Nevertheless. And we'll see how that may happen. But nevertheless, that's the slow evolution. Same thing for the Earth. I don't know of anyone that can do a back-on-the-envelope calculation and come up with 700,000 years.
Isn't that just a half-life? I mean, it's a stochastic process, the reversals, and then you...
Good. That was not prepared, but thank you. Well, that's how we'll try to interpret it. But then, stochastic means that you have to put something else. I'll come back to that. The funny thing is that when you plot all the reversals on top of one another, they have that same shape. This is decaying and this is growing. All right? So it decays with the characteristic time of decay here is just Joule dissipation. Okay? It's in that case it's an ohmic time of decay. And the growth rate here is much faster. And again, you see the slight overshoot. This is not unlike, again, among the features it shares with the Earth, it's not unlike what people have been able to reproduce for reversals in the Earth, where time goes backwards for these guys. It decays slowly and then it grows back again with a much faster amplitude. Again, in the Earth type of things, this time scale is of the order of the Joule dissipation in the iron core, of the order of, and this is a much faster process. One note about the reversals is that when you hit the point where you have those regular reversals, all right, you change the temperature a bit. Remember, changing the temperature in this system is like changing the magnetic Reynolds number, because the conductivity is a function of temperature. All right, temperature here is just another way to change slightly with the conductivity, which you cannot achieve with the others. So you go from here to here by changing the temperature. Your control parameter is the magnetic Reynolds number.
So how it changes when temperature changes by 20%?
You go
what's
from
the change
this.
in Rm? What's the corresponding change in Rm then? Rough, sigma. Let's say sigma.
8%.
8%.
Can you keep that constant by heating? Or?
Oh yes, most of the time the temperature is controlled. When I do this, is because I let it run.
Oh, okay.
No, the temperature is.
But the reversals are not due to heating up in the dynamo active state?
No. The reversals are so. This is an important feature, because one of the ideas that could be, and I'll come back to this in detail, one of the naive ideas that people can have, which is not necessarily wrong but not entirely correct, is that you heat the reversals like the one here. They're located in phase space in the neighborhood of that transition. All right? So what you may want to say naively is, all right, the flow is changing, is pushing the dynamo like this, and the dynamo reverses, right? Because it's got big fluctuations. Now, when you're changing the temperature only, you are not changing the hydrodynamics. For the viscosity, for the Reynolds number, I know the viscosity is a function of temperature, but the difference between 10 to the 7 and 10 to the 7 plus 5% is, all right? So it is located in that window, and the reason we know it is that we've changed. I told you about changing the ring, changing this, changing that yesterday. When you change the precise location for the theta critical at which that transition takes place, the region for which you observe those reversal changes as well. Okay, but you can affect the reversals without changing the hydrodynamics. Means it's complex. There's just not one very simple explanation. I'll show you the one we've understood, but it's not. I thought I didn't want that slide. All right. Here's another stuff. Is you're increasing theta, you're into an oscillatory regime, and when you go from theta equal to 0.4 to 0.6, that is one increasing the rotation of one with respect to the other, you get a time series where the oscillation happen faster and faster. Okay, and if you plot both the way the amplitude vary when you cross. So you're in a line where you have a stationary dynamo with a high field. It keeps a stationary dynamo until it decreases, all right? And at that point, you hit a bifurcation where you're growing again an oscillatory dynamo. The period diverges into an oscillatory regime with a bifurcation for the frequency, but a continuity for the amplitude. There's a bursting regime which I like so much. So you see there, and the field does a 100-fold increase. At the point where I'm measuring things, it is here, okay? So it says that maybe 10, 12 centimeters from the axis. Now with the new measurements we've had recently, when you're getting closer to the axis, the field gets to be almost a kilogauss. Okay, that's a bunch of fields.
No, I'm sorry. In this time series, what is the magnetic diffusion time and what is the kinematic time scale?
So the kinematic time scale, that is the way at which you're churning the flow like this, is 20 hertz. All right, it's small. Okay. Now the diffusion time scale is of the order of a few seconds. Okay, so it's you can take it as being one measurement of the width of that. Okay, because as I told you, as in reversal, it won't grow and decay in times that are much different than that. And the time in between is random. Okay? I don't know. Does anyone know of an example of a bursting dynamo in natural medium?
Numerics and also sometimes a fit.
Hey, nice.
Most of the stuff we found we also find. These reversals and also these bursting things.
If you have a reference for the bursting one, I'd be very happy to read about it.
Try to produce one.
Because this is for me, this is absolutely amazing.
I don't know if it happened somewhere on a planet or something like that.
Anybody knows that in real life?
Axel, Reza Travakov's paper with stochastic, they had something like that, didn't they?
These are mean field models.
Yes.
I mean, MRI looks a bit similar. If you have a strong net field, then you get also strong spikes.
I'm willing to write down reference if you can have. So we have an example with liquid sodium and solid silicium, right? Is the two configurations that do this. They have interesting properties. The spectral density has a very strong -2 scaling law. Okay, the histograms of these things have long tails, and all sorts of correlation. The correlation here just says basically what I was telling you, is the half-life, is the diffusion time. So how long do they last? Roughly one diffusion time. Their spectral content is -2, which is fun. I mean, it's not so easy to understand. And this long Poisson-like wings on
Because the -2 is discontinued, right? In time.
Wouldn't that be -1?
Discontinued
Is this is the heavy side where it transforms is -1, right?
in one dimension.
In one dimension. Here's another type of other bursts, just for show. I mean, you let the experiment go, or you do nothing, and it does that. And, not really sure what I get out of it.
So is that what's your theta?
Here it's an increased theta compared to the reversals. It's in the second packet of dynamical regime. I'll come back to that. And now there's the interesting point of reducing the velocity of one disk to 0 to have only one disk rotating, because one disk rotating is a bit of a small, it's a pocket Riga experiment, right? The fluid spirals towards the disk and comes back, and well, it's interesting to see what that limit is. So here is now the evidence we have here is for strong bistability. So what I observe here, I have to tell you which path I'm using to get there. All right? So path number 1, I am fixing the velocity of one disk, okay, and I'm reducing the velocity. No, I'm sorry. Path number 1, I have one disk equal to 0, and I'm increasing progressively the velocity of the only rotating disk. Okay, so it's driven by the rotation of one disk. F1 is equal to 0. I have no dynamo, non-dynamo, grow a dynamo where the field looks like this, increase again, and that's where we stop the experiment. I don't know what happens after that because I cannot rotate a disk faster than 27 Hertz. Okay? But that's the behavior you see. All this transition here is stationary. You always, so if you rotate just one disk, that was surprising because Riga fields an oscillatory field, right? If you rotate just one disk, you will get a stationary dynamo only. Now, if you keep one disk fixed fast, all right, pick any point that I had before. So pick a rotation like 22 Hertz here, okay? You know that in the limit of F1 equal to 0, you have that stationary dynamo, but starts from a point where you are having an oscillatory dynamo when they both rotate. Okay? So here is, I have, when they're both rotating, I have an oscillatory dynamo, and I'm slowly going to F1 equals 0. Okay? In which case, I keep an oscillatory dynamo until I kill it. Okay? Now, if I have an oscillatory dynamo, and I just bump a little one, the frequency of the other, I keep an oscillatory dynamo. All right? Now, if I make a little drawing, along these lines, I'm transiting from stationary to oscillatory. Here, I'm no dynamo to stationary dynamo. Here, I'm oscillating, and if I go this path, I keep the oscillation. So I have one region of parameter space where I have a stationary dynamo if I started from F1 equals 0, or an oscillatory branch if I started from F2, F1 not equal to 0, and decreasing it. Okay? And those lines are fixed. I'll talk about it. Right. So it's a strong bistability in that region of space. It's here. Keep the oscillatory here. It keeps oscillating, and I can come back a little bit and keep an oscillating dynamo. But if I increase here, I will see a bifurcation here from no dynamo to stationary dynamo. All right? So it's the picture we have. And the final thing.
Stationary, you said. Yeah?
Which one?
And you go horizontally outwards.
Horizontally, you go no dynamo, stationary dynamo. Okay? So when you increase one parameter like this, we've always observed a transition first to stationary dynamo. So here you move at a constant theta here. You increase, you have no dynamo, stationary dynamo, oscillating dynamo. No dynamo, no dynamo, no dynamo, stationary dynamo, oscillating dynamo.
Yeah.
Okay? And it's always like this. You go no dynamo, in that little region of space here you've got the reversing dynamos, but they're always found first with the stationary dynamo. Yeah.
Is your flow pattern always like the one at the bottom?
When I do what?
When you hold one stationary and
Yes.
increase the other?
Yeah. When you move that path here.
No, when you're going on the bottom.
When it's that one disk pattern. Yes. This one's continuous here. So this is the stuff. So this is the regular dynamo here when theta equals 0 I described yesterday. This is a low field dynamo that happens in a pocket where they're very different. And those are the transitions that I showed you, where you can have the magnetic field being continuous when you go from stationary to oscillatory, or you can have a jump when you go from stationary to oscillatory. Okay, it's this kind of behavior. Finally, when you increase F1 minus F2, whatever the sum F1 plus F2, you always go from I fields, and then you decrease. You have a pocket with very low dynamos. Then you go into a second pocket of oscillations, and then you go to the one disk case. All right. And when you go to regimes, here when you hit the first pocket, it decreases like this for the frequency of the time-dependent regime. Here it diverges in here, and those functions here are 1 over square root time. For some reasons. Come back to this.
Another question.
One question.
Yeah.
No, I wanted to point to you.
The average value of B in those different modes of dynamo is the same? Or
No. It's here. You see, you have fields with. This is the intensity of the dynamo you get when you increase the imbalance. And this is the frequency of the time regimes. Okay? So you can have stationary, here is stationary with a high field. You can be stationary with a low field here. And you can be oscillating with a high or low field. Alright? So it's that picture we got, the zoo. Alright? When it starts looking a little less than a zoo is when you start thinking about transitions between these regimes. And, well, it's in French, but I'm sure you can understand. So one disk here, in that sequence I'm showing you, one disk is rotating at 21 hertz, the other at 15 hertz. Then, when you go from black to blue, one is just rotating a hertz faster. From blue to green, you've just changed the temperature a little bit. And then if you reduce the velocity of one disk, you'll have those oscillating modes. All right? So the feeling is that you're in a pocket there. When you change things a little, you change very much what you see. Now, if you've done enough dynamical systems in your life, immediately when you see this, you want to plot x at t plus 1 as a function of x at t, right? Immediately from these patterns. And when you go, when the black one draws the picture you have here. So the magnetic field seems to be going this with 2 points where they seem to be more often is this one and this one. Of course, B and minus B are solutions, right? So if you have a fixed point in the system, you're going to have the opposite fixed point, just by nature. Well, the blue one starts from, this one is trivial when you just look at it like that. It starts from a point where it sits most of the time and you do a large exertion with a burst of field. Right? Now if you put the two on top of one another, well, the point where it starts is that fixed point you had before. So in the language of instabilities, when you start from here, you can do a homoclinic orbit and come back to it, or you can do a heteroclinic orbit and do a cycle, right? And now you have the reversing things, and the reversing things go from one state to the other state in a limit cycle. All right? That's what you get from this picture. Here is the last piece of evidence. You start with the configuration where they both rotate at the same speed, all right, and you decrease the speed of one disk, so you're making F1 minus F2 increase, and you go that sequence. That's the dynamo for equal speeds, and here I'm plotting the radial field as a function of the toroidal field, all right. So what I do is I progressively decrease the toroidal field, okay, until I get the toroidal field almost equal to 0, and the field is mainly radial where I measure. So abusively, I'm going to call the point I start with a dipole. I've shown you plenty of evidence yesterday. I'm calling that one a quadrupole. All right, and then so I'm going from a dipole field to a quadrupole field, and then if I start hitting on it, then up to a point, if I continue decreasing, I will hit a limit cycle. All right? So I have a bifurcation where I go here, I move the stable fixed point in that parameter space until I hit a limit cycle. Now, once you've done that, everything here spells low-dimensional dynamics. All right? Once you've reached this point, all you feel like doing is writing a nonlinear equation coupling mode and see what it gives. There's a very large list of this. I'm putting up a few references here because I don't know. Was Riki Take the first one? I'm not even sure. Of somebody that devised dynamo with mode 1 and 2 and start writing d1 dt equal d2 dt equal. So here's a list of reference. It's incredibly partial because there's way more than that. It's the one I've read in some detail, enough to write them down here. And very partially again, I will concentrate to the work of friends and all the stuff we've done recently. But this is, okay, this is an arbitrary choice because it's what I like, right? It's because at this point you could... All right. So I'll repeat for Matthias. So my understanding, I'll repeat just what I said yesterday. My understanding of how VKS dynamo operates with a ferromagnetic impeller is the... Wow, I've never been able to draw that. And here is a disc. I'm not putting the blades because I won't be able to draw them. There's blades on top of them. Okay? I can't draw them. Now, my understanding here, based on, as I said yesterday, numerical experiments and experimental measurements in the lab, is that if you have a magnetic field like here along the axis, then the fact that this is a ferromagnetic rotating disk plus the shear here amplifies a strong toroidal field. Okay? This is locating an omega effect near the disk. That omega effect is further amplified by the fact that the flow is strongly diverging on the disk, because one rotating disk like this is a centrifugal pump. Okay? The combination of these plus some amount of alpha generator in the neighborhood. Okay, you can think of alpha as many ways. When you talk to people, they like to think that since the fluid is radially expelled outward by the blade, okay, and rotating as well, you'll create swirls like this. What I've explained yesterday is I don't like particularly that explanation. I prefer to rely on our measurements and Karl-Heinz calculation, that if there is a gradient of u squared in the neighborhood, then you have a mode which is capable of generating an alpha component. That is, a component of current which is parallel to the d theta field. Again, I am not sure that helicity has to be involved in there. It's the structure of the turbulence and stuff. Okay. But if you have that alpha current here, you regenerate the magnetic field line. So the rotation, as we've seen at the experiment, the rotation of one disk alone produces a dynamo, okay, and it produces a stationary dynamo. Okay.
Can you explain, you said that the diverging motion amplifies the omega effect.
Yeah.
What do you mean by that?
Well, if I put a fluid line in a field like this, if I put a magnetic field line
it's
in a velocity field that is diverging like this, that's a good amplifier. No, right?
Yeah, but you require that the monopolar field in that projection. You have a velocity field which is monopolar outwards, but not necessarily a magnetic field.
There's an inflow in the middle.
No, I'm saying that.
Yeah. So the flow is like this, but the magnetic field could be.
No, I'm saying
the arrows could be opposite direction. Could be non-axisymmetric.
All I'm saying is that if there's a b theta component here, because of the outward flow, it will be stretched a little bit further. That's all I'm saying. The equation says that there will be a d theta.
Yeah, the divergence. No, it's not a divergence term. What is it?
We'll write the equations that really work. It's a very good example of a magnetic field amplifier in 2D.
And the gradient u squared has nothing to do with an alpha. It's a pumping, if anything.
Among the mess of the terms that I've showed you yesterday, I'm sorry for the word mess, but the very many terms that I showed you that can contribute to the electromotive force. One says you have a gradient of turbulence intensity that has a projection onto it. And that gradient of turbulence intensity, we've measured that effect and we've seen it. Okay? So, but then it's a matter of taste. I'd rather use that whose magnitude I know to be right, as opposed to this scenario, which I'm not sure happened. But then, so I require, and the last argument I had yesterday is the finding by Andrei Giesecke in Dresden and his colleague, that if you do this, the amount of alpha you need turns out to be alpha for critical is the order of u divided by 100. Okay? Whereas if you don't have that, the alpha you need is huge. Okay?
Regarding this outflow, there were solutions, right, of the induction equation, which show that the flow, incompressible flow of this form, which you have here, is very good generator of magnetic field, right? Sweet solution, I think. There were also solutions for the Hubble flow of Zildovich, Rosmaikin, and so forth. So the flow near the propeller will be moving towards it along the axis and then flowing out in a roughly cylindrical symmetry.
So, bear with me a second. I'll be happy to discuss that again tomorrow, but bear with me with a second. In that scenario, at least, I have the rotation of just one disk, as observed, generates a dynamo and it generates a stationary dynamo. Okay? So what I'm viewing here is a scenario whereas if I rotate the disk, I can generate the field each of the rotation here with the fluid is able to generate a dynamo, and since for each of them B and minus B are solution, I can generate the red arrows or the brown ones. Okay? If I generate the red, I call that the dipole. If I generate the brown ones, I call that a quadrupole. This is abusive, but this is what you feel like doing. And then, of course, the next thing you want to do is you want to write d of dipole dt is a function of dipole quadrupole nu d of quadrupole dt, and it's not even sure that u is necessary, because if you have two interacting dynamos here, you can produce a lot of dynamics without invoking change in the velocity. Okay, and that's what I'm showing next. So the model that goes like this is the one that is due to François Petrelis and Stéphane Fauve, and is a very, the idea now that I'm put myself in a frame where I see all evidence of low-dimensional chaos, and when I go to the mechanism, I have the feeling I want to say this interacts with this. Okay, and once you do that, what you want to write is you have a dipole and a quadrupole, so you introduce the amplitude of these two modes. There's a complex amplitude, and you want to write an amplitude equation for this. So you go dA dt equal. Now, what you know is this thing has a B minus B symmetry. All right? So when reversing B to minus B, I'm reversing the dipole, but I let the quadrupole unchanged. Okay? So it means it has the symmetry of A having to be invariant under A to minus A conjugate. If you do this, you end up with an equation that looks like this. Oh, it's there. Plus beta 1, blah, blah, blah. I wrote it there, so I don't need to copy it. Okay? Now, what you know is all the coefficients here have to be related to F1 and F2. Okay? When you start from F1 equal to F2, you have the symmetry with respect to that plane here. Okay? So when F1 is equal to F2, you have a symmetry by the plane, which is the mid-plane, okay, perpendicular to the axis. So it's here. That mid-plane, which goes through the center here, is what I call an R-pi symmetry. Okay? Now, in that case, I know that the dipole grows. All right? So the growth rate of the dipole is the real part of mu plus the real part of nu, and the growth rate of the quadrupole is the real part of mu minus the real part of nu. Okay? So at least I know that this thing has to be positive, because when they're equal, the mode that is growing is the dipole. Okay? Now, what happens when I start having F1 not equal to F2? All right? You have to play with the coefficients and modify it in order. That should be enough. So if you take the simplest case, if you try to make it as simple as possible, then assume that beta 1 real is beta 2 real is beta 4 real part is equal to 0, and you want beta 2 real part equal to minus 1, because at least you need to keep a saturation. I'm not just defining any of this. I'm cutting through that equation to get a simple behavior. All right? Now, once I've done that, again, you remember in the path I was starting from a dipole, I was gently going to a quadrupole when I start increasing F. Okay? So I want a gentle change like this. So I'm saying that, okay, the amplitude of the field may not be changing so much. All right? What will depend here is when I write dipole plus quadrupole, the amplitude is not going to change when I go from dipole to quadrupole. I will change the phase of that complex number. Okay? So I write this equal to rho exponential I theta plus theta naught. Okay? And then if I do this, I plug it into the equations I've derived with that approximation. I end up to theta naught is equal to mu I minus rho sine 2 theta. Okay, it's just plugging this into the equation with these approximations. Okay, so that's the equation for the phase. Of course, you see where the theta naught comes from is because you will have a marginal state only when you can invert sine 2 theta equal mu I over rho. Okay? And when you will hit a critical value when mu I over rho, depending whether it is greater than 1 or smaller than 1. Okay? Now, once you're at that regime here that allows a solution theta critical equal to mu I over rho, you're in a solution where there's 2 unstable fixed points. Okay? And 2 stable fixed points, as long as rho is less of the critical value. And what you have is the system has an unstable global fixed point, which is b equal to 0. It will have to go to one or the other. One is stable, the other is unstable. All right? And what happens when you change those parameters is that those 2 fixed points are going to collide. You have the collision of a stable and unstable fixed point, and that is known to create a limit cycle. All right? So you exactly describe that. You change the phase. When you change the phase, the fixed point moves. It moves away from the dipole onto the quadrupole, exactly as I was showing you. You start from here, and then you go here, and then you go here. You hit the quadrupole, and at some point you will have to start the cycle. Okay? And the cycle is because those 2 things go near, and they're going to collide in that picture. All right? Now, what do you get intermittent reversals? Is because you can go from here to here. If a fluctuation, because now the flow was nicely smooth in what I described. If there's a fluctuation, if there's noise applied to that set of equations, if a fluctuation brings you to the unstable fixed point, the unstable fixed point shoots you here to the other stable fixed point. All right? And you reverse. Now, it's important to understand that the trajectory that connects one stable fixed point to the other stable fixed point is a deterministic dynamics in that picture, right? Here you just hit the low dimensional dynamics. Fluctuations, again, will bring you somewhere else. And as you see in that pattern, before you go back to a dipole value, you have to overshoot. Okay? Because you cannot go directly. There's no connection from here to here. You're shut by another unstable fixed point. And that's basically what one sees. So you implement that system, you fix the coefficients so that they look like the simulation. Of course, it's a normal form equation. In a normal form equation, there's no way that you can derive the coefficients, right? It's what the symmetry is and the dynamics is telling you. You implement that and you find something which is pretty close to what is being observed. All right, so that's the model on low-dimensional dynamics that has been devised by François and Stéphane. What I'm saying is that it's pretty justified once you've decided that your dynamo is this kind of interaction, and indeed it reproduces a number of behavior. So one question we've asked with Roberto Benzi last year is the following one. When I said I needed fluctuations to go from one to the other, is it important that these fluctuations be turbulent fluctuations, or could they be just any fluctuations? In other words, in that dynamics, all right? So because the picture you had, which probably you thought about, and I haven't said it either, is stochastic resonance of some sort. All right? You're onto a stable fixed point, and you're counting on your noise to send you to the other fixed point. Right? So now the time scale in stochastic resonance is given by the variance of noise, as we'll see. Okay? And so you say, is it important that that noise be Navier-Stokes noise, or could it be just any noise? So in order to answer that question in a limited amount of time, we've reverted to something that is known as shell models. So in the shell models, they may be or may be not popular in the hydro community, depending who you're talking to. You replace all the velocity field by 1D components that are interacting in shells with the nonlinear term, and you do the same thing with the magnetic field. I know, there's no more geometry. All right, you're losing all the geometry. What you keep is the fact that the spectra have the right Navier-Stokes k minus 5/3, k minus 11/3 spectra. All right, and you can play a very low Prandtl number game. Okay, because basically you decide how many shells you put on each of them. So since the ratio of the shells you put in B and U is the Prandtl number, then you do, okay, I can create a noise that has many characteristics of turbulence which I can apply to the magnetic system. Okay? And it's all, and the fact that shell models give a good noise with respect to hydroturbulence, that has been proved before. And you look only at the large-scale magnetic field. For the large-scale magnetic field, what you write is, you write an equation where it has a deterministic dynamics. You give it to the flow. You've lost the geometry, so you lost the dynamo generation, right? So you're going to write dB dt is B minus BQ, all right? Just for something. It's an equation that has a bifurcation to B2 equal non-zero state. And then you will have, acting on it, all the fluctuations that come from the nonlinear transfer, which are due to the turbulent flow. Okay? So it's a first-order test of what the nature of turbulence is.
So this B2 equation is, why? Is that the forcing kind of thing? Or?
Yeah, it's the forcing kind of thing. I'm putting, in the shell model has an inverse helicity cascade, so I'm going to build a dynamo. Mm. Now, to that dynamo, I give the features of the low-dimensional dynamics I want. Okay, because I got rid of the geometry, so I'm building a large field with a characteristic I like. Okay, yes. But the noise I apply on it really is turbulent fluctuations. So it's turbulent fluctuations of a self-consistent manner onto a deterministic dynamics. And what you see, sure enough, is that it reverses, couldn't do anything else. Okay? But the important point is that now the time scale for which it stays and the time you have between the reversals, right, which is much longer than the diffusive time, as observed in the experiment, that time comes from the dynamics. All right? And that time varies when you change. Here we've changed the magnetic Reynolds number. Because it's easy to do in the simulation. Think of it as changing the magnetic Reynolds number.
So in the F2 term, you take more than just U2 and B2. You just take the entire spectrum.
Yeah. Yes, in the F2 term, there's the entire spectrum. It's the nonlinear term that is self-consistent with these equations.
Oh, I see.
It's a little.
Oh, I see. It's just the usual. Yeah.
But you can convert that into a mean field theory. You can say, all right, that F2 term, all right, has a component which is proportional to B2 that Roberto calls beta, but it's an alpha effect in our language, plus all the nonlinear transfers. So if I'm assuming, and that's the idea of this, if I'm assuming that the equation is this plus noise, then immediately you have stochastic resonance, right? Immediately your picture is that this has a fixed state equal to the square root of beta over am. Okay? And you're applying noise, so you're jumping from one to the other. Stochastic theory says, all right, what is the time in between reversal? It is a time that is controlled by the variance of the noise. Okay? But now the noise, so this is fairly well understood, except that this noise here is non-trivial. It's hydro type of noise. And what you find is that the hydro type of noise has a very strong influence on how that noise varies with the Reynolds number. That is, you can make tau really large depending on Rm values. Okay? And this is not the given thing. If you take a Gaussian white noise, this is not what you find.
For real alpha, you would have an I in front of the beta, I think.
Yeah, but it's the imaginary. You're retrieving energy. It's the complex part of V2 you're looking at, really. I'm willing to discuss that in more details. So, what we get of those two experiments, once you've drawn that low-dimensional pattern, is that first you can understand the dynamics by a coupling of modes. And I think I know why there's this discrete number of modes. And then that the transition in between are governed by the turbulence, and so is the alpha effect. So the alpha effect, to first order in all these things, the turbulence does two things. It generates the alpha component you need in order to build these fields, and it also decides how the dynamics proceeds in time. So I come to the end of what I wanted to say. There's a few open questions. What is the link between those large-scale instabilities I was describing and how turbulence varies is something that for me is completely open. How does the saturation proceed? Well, if I'm going to have fields of 1 kilogauss inside the system, what does it do to the velocity gradients in order to stop the growth? Wow. And there's the last one which I very much like to know is pi. If I plot the power I have to spend in order to reach a dynamo as a function of the intensity of the magnetic field I get, I'll find that for a range of powers that go between 50 and 120 kilowatts per motor on the average, I can generate fields that are more than an order of magnitude different in its intensity. So, and that tells me maybe when we do scaling of magnetic field energy versus this and that, maybe we should be careful on what type of field we're talking about, what kind of dynamics is underlying them. For instance, when you have the bursting thing I reproduced, there's a change of about 20 kilowatts in the energy which is spent per motor. This is 1/3. I don't know if that's realistic. So those measurements here, they come from just the power consumption of the electrical drives, which is not a very good indicator of the actual mechanical power consumption. So the run which is being done today has installed torque meters. And we're going to measure this in more details. And thank you. This is all the people that have been working on this over the years.
Mm-hmm. Thank you.
Question, please.
Professor, with these reversals, right, you somehow were making many excuses that you don't want to compare them with the geomagnetic field. But why not? For example, for geomagnetic field, the statistical properties, the idea of the intervals was discussed, the fractal dimension of these black regions was discussed. What else can you do? Well, it's not clear how informative are all these measures, where indeed they can tell you about it. But so why not doing? Have you done similar analysis? Is it similar? Is it dissimilar?
The point that is clear is the following one from the experiment. So your question is, let me track back your question. Question number one is, what have we learned by doing all this?
Yeah, it's unclear. Yes, it's unclear from the outset.
So what we've learned, what is sure that we've learned there is that if you have interacting dynamo modes, you can create a zoo of dynamo behavior, some of which have regular, irregular, and this is interesting because I'm not invoking. I don't have to change the size of the planet. I don't have to say that I have a double layer convection in order to go from this planet to that planet. All I have to do is determine which parameter range I am in very simply interacting mode. And those are as simple as it gets, because that is just R pi reversible or antisymmetric. It's a symmetric antisymmetric competition that is giving you this. Right? So that's, and the fact that you can grow these, but it's been shown by Chris Jones as well in the numerics, people know that you make, every time you have a dipole, I'll have a quadrupole nearby. All right? So the result is, if you have a dipole and a quadrupole nearby, and you bring them within interaction range, then you get all this. Okay? It's not, it is not so trivial. A few years ago, I'm not sure that it was such a widely accepted view. The second thing, now the question, so for dynamo mechanism and stuff, we've learned that all these actually make sense at Reynolds number equal to what it is. Okay? And which is the same range of as many natural bodies. Now what you want to know is how much of these can I apply to specific dynamos like the one of the Earth. Mm-hmm. Now, regarding the comparison with the Earth, the two solid features are the dipole goes down when it reverses, okay, and the time scales involved for decrease and increase are resistive time scales. And whether we like it or not, again, in these things, the resistive time scale that is involved is the molecular one. There's no correction to turbulence in that case. It's a diffusive time scale. Now, how do I compare further a cylinder with two propellers to a planet with a core, convection, and a huge rotation rate?
But there can be universal properties. For example, all of a sudden, you will have a similar PDF. It's all waving my hands. But unless, well, those who don't take the risk, right, as we all know, they never drink champagne.
There was a suggestion to associate the differential Fs with differential rotation, or maybe the Coriolis parameter or something of rotating stars.
That's what I said. Another thing, so some of it is. Oh, sorry, my phone is broken, so I can't keep it from. Some of it is pleasing to people. For instance, the fact that, what was that? The fact that increasing F changes the periods in between the oscillations is something that is has been published several times for stars. Actually, in non-dimensional units, I got a plot which I don't show where it actually is in the good neighborhood. All right? But then again, you're making, you know, I think it has something to say. I think there's a very, my personal feeling is that there is a strong similarity between what I've shown from an experiment like this and what people have been describing here for the sun, the galaxies, and the rest. I think the mechanism we're talking about basically the same one. So I think there is some similarity. Now, how do you extrapolate from one to the other? For instance, how do I go from 100 seconds between reversals to 100,000 years?
Oh,
you know what was the biggest hit of the experiment, the most success I ever had with the reversals? The community that has been constantly on the phone trying to talk to me, invite me everywhere, is the fundamental Christians.
Fundamental?
The creationists. The creationists have been on the phone day after day inviting you to the most extravagant places because if the field reverses in 100 seconds and I do a scaling I like, then it's all right. In 7,000 years, I have all the bending in the ocean floor. I don't need long-lived Earth.
No, but Jean-François, I'm talking about a different thing.
You see, are you serious? This has been a very important concern. I can show you paper articles where people publish that we've solved the case because the geodynamo is one of the biggest problem they have. It's a huge problem. It reverses. It is known. This is proven. So all you have to do is change the time scale. Changing the time scale is something they have successfully done for carbon-14 dating, as you know. They've published papers in the same journals that you and I read, where it says the huge mistakes in datation because the rate at which the half-life is a poorly understood thing. It's wrong, but it's been published in the same journals that you and I publish papers in.
No, but I'm not talking about that. Not about comparison with that.
That's just my job.
For example, it was indeed, people spent quite a lot of time discussing the statistical properties of reversals. And to me, I was also problematic was, okay, fine, we will calculate your fractal dimensions. What have you learned? God knows what. But you have an experiment. You can now indeed meaningfully address this question. It's changing parameters and say, and find out if the fractal dimension is indeed a useful diagnostic of anything.
Well, I don't think, I mean, if you want, my
or
opinion,
what else?
My opinion is that it's not much use, but what could be useful is a reversal connected to stochastic resonance between states that are just as in the model, they're just deterministic states. So is it true that you have deterministic states and all what fluctuations are all about is in the time dynamics? Mm-hmm. And that, of course, as you know, has particular scaling laws, and that should be. But all we can do at the moment is measure 100 reversals a day. So if you want good statistics, you need a month of doing just that.
Come on, 100 is a huge number.
No,
in comparison with the number of reversals we have from geomagnetic records.
But then in that case I could produce plots where it's all in agreement. If you need another science paper, we can write the plots, put them together, and go like we got it covered. If you know the right editor and you got good friends,
well, come on, Gary Glatzmeyer had one reversal in his code, and everybody was discussing it.
But
right?
Gary achieved something which is just as significant as what Agris and the others did back in 2000. He's showing you that if you put the equations, you indeed see a reversals, even if the parameter is those fantastic achievements. Now matching with poorly resolved statistics, which you could have, because at least in the astrophysics, when you have that number of statistics, that's what you have. But in my experiment, if I publish poor statistics, it's valid that you tell me, just so why don't you go back and converge those curves, and when you've done that, you show it to us.
But are you doing that? Will you show it to us?
But
we run 5 times a year. So we'll do this. It's one of the things I want to do.
But where is problem? These excursions are the result of large fluctuations. Probability of large fluctuations is exponentially small, and because this time between reversals is much larger as any constant in your equations, and I see no problem to discuss anymore.
That means that what you're describing is a large deviation theory of the fluctuations, and that's fine. It's a theory. As Anwar was saying, once you have the experiment that does that, why don't you go ahead and verify that theory? Because what you say has properties. The time in between goes like exponential minus, I had it, minus A, which is the height of the potential well, over sigma, which is, it's this, huh? Right, you here, this is the height of the potential. One fluctuation with that variance sigma is going to get you there. Okay, if this is the theory, that has a very well-defined theory, as Anwar pointed out, there's scaling laws that you can verify that. So maybe we can show that it is this, and in that case, I agree with you, it's closed.
So the only difference is that this potential well is multidimensional, and it is not so defined as you draw on Pictet.
Yes. Yes, but large deviation theory says it doesn't matter. So the question is, does it matter or not?
But nevertheless, maybe that it is not exactly exponential value, but nevertheless explanation why these reversals are so, why you should wait for reversal long with respect to another time scales in your experiment, it explains, and there is needed, so of course, very statistical analysis of all these excursions.
So why is it so I'm willing, I kind of agree with you, but then the question is, why is it short for the sun?
No.
So how do you make it small? For the sun it's 22 years. 22 years is a short time compared to all the rest. What?
No, on sun there is almost periodical.
But it still has a time scale.
It's not induced by fluctuations.
But
It's not induced by fluctuations.
No, it's not induced by fluctuations. Although these fluctuations are present.
Yeah.
yes, for instance, the Indian mushrooms also are semi-periodic. Looks like periodic, but the basis of all clouds going in different directions are not so easy. How to say in English? You cannot say at first that they should go exactly so, but the total event, the sum of all this looks very periodic.
So it is what we're proposing here. There's a model in which the generic features is a deterministic evolution, but on top of that deterministic evolution you have a small noise that plays a role in doing the stochastic transitions or pushing you from one orbit to the other. So that's what we get from the experiment, and in that particular frame, I agree with you. All right? Now, I don't know if I'm ready to extend this observation to, well, it's well understood that it's always like this.
I mean, what is the distribution curve of waiting times? Do you have one?
Not one that I'm willing to show.
Because it's uncertain.
Yes, because it's uncertain, and when you look at it, it looks so much like some of the things that have been published for the geophysics and all that, that I think we should resolve it. I'm firmly against, I think we should do the homework right, run, see 1,000 reversals, do the statistics right in which parameter space, how does it change with RM, delta RM, describe
Wait a
that.
minute. Don't have more reversals than observed for the Earth.
Well, but I have an
Because
experiment.
otherwise you will be comparing very different things.
But I have an experiment. When I read papers in astrophysics and people say this argument is correct within an order of magnitude, which is often the case, and you can feel happy. An order of magnitude, given everything you have to measure, is a fantastic feat. If I send an experimental paper and I say, well, I get the value within an order of magnitude, the referee won't even read it, right? I'll immediately give it back to
Suggest me as a referee.
And say, all right, you claim you measure, first thing you do, you measure indeed, and then you come back to us. And I think that's fair. That's fair. That's why an experiment is useful, is for getting more data. So it looks like what is for the Earth.
Yeah, you said that between the reversals on that phase space, the trajectory is deterministic. Right?
It's the thing that connects you from one to the other.
Yeah. So, for the predictive power of those kind of models, we could actually think that between reversals we can somehow know what the field is doing, right?
No, it's the other way around. It's between reversal, you sit there and the noise is doing that. It's only when you reverse that you hit the deterministic line.
So we know how the field is going to behave when it begins to reverse.
Yes. Yeah, because once you hit the unstable fixed point, then the deterministic part takes over.
Yeah. But the initial condition will be always different with different paths in the phase space.
But even if that is correct, it denies that if there's a deterministic evolution during a reversal, I'm sure it's something that people will be happy to know.
Okay, let's finish for now. Thanks again.